Hello and welcome to Math Zone African Motives. In this tutorial, we will be diving into some key applications of differentiation. Let's first take a moment to look at the module summary. This will give us a clear roadmap for what we're going to cover. Our module focuses on the practical uses of the derivative. We will be exploring 4 main applications. Understanding each of these will build a strong foundation in differential calculus. First, we have Newton's method. Second, we'll look at optimization, which involves finding maximum and minimum values. Third, we'll cover related rates of change. And finally, we'll apply these concepts to motion in physics, looking at rates of change in motion. We'll tackle these topics one by one. By the end of this module, you will be able to apply the derivative to solve real-world problems. Let's begin. Our first topic is Newton's method. By the end of this scene, you will be able to use Newton's method to find better approximations for the roots of an equation. Newton's method is a technique used to find better approximations for the roots of an equation. Remember, a root of an equation is simply a value of the variable, often x, that makes the equation true. Graphically, it's where the function's graph crosses or touches the x-axis. Let's say we have a function f of x. The roots are the x values where f of x equals 0. The method starts with an initial guess, which we'll call x sub 1. We can get this first guess by graphing the function and seeing roughly where it crosses the axis, or by finding an interval where the function's sign changes. Once we have our guess, we use a specific formula to calculate a new and hopefully more accurate approximation. This formula, which we'll highlight in blue, is the core of Newton's method. It says the next approximation, x sub 2, is equal to the current approximation, x sub 1, minus the function of x sub 1 divided by the derivative of the function at x sub 1. Let's break this down. The term f of x1 over f prime of x1 represents the distance we need to move from our current guess, x1, along the tangent line of the function to reach the x-axis. This new point on the x-axis is our improved guess, x2. You can visualize this process. We start with a guess x1. We find the point on the curve directly above it. We draw a tangent line at that point. We find where the tangent line hits the x-axis. This new x-intercept is our second guess, x2. Notice how it's much closer to the actual root. We can then repeat this process as many times as we need to get to the desired level of accuracy. By the end of this scene, you can now explain the fundamental process of Newton's method. Now let's apply Newton's method to a concrete example. In this scene, you will solve an equation using this iterative process. Let's work through a typical problem. Remember, we need an initial guess to get started. The question asks us to use Newton's method to find a root of the function f of x equals x squared minus 2, correct to 2 decimal places. First, let's find our initial approximation. We can use a sign change. Let's check f of 1 and f of 2. f of 1 is -1, and f of 2 is 2. Since the sign changes, there must be a root between 1 and 2. A good initial guess, x1, would be the midpoint, 1.5. Next, we need the derivative of our function to use the formula. If f of x equals x squared minus 2, its derivative, f prime of x, is simply 2x. Now we can write down our formula. Let's make it more general for any step-in. The formula for finding the next approximation, x sub n plus 1, from the current one, x sub n, is x sub n minus x sub n squared minus 2, all over 2x sub n. We'll start with n-1, using our first guess x1 equals 1.5. Plugging in 1.5 for x1, we get 1.5 minus 0.25 divided by 3, which calculates to approximately 1.4167. This is our second guess, x2. Now we repeat the process. We use x2 to find x3. For our second iteration, n is 2, and x2 is approximately 1.4167. Plugging this into our formula gives us approximately 1.4142. This is our third guess, x3. Let's do one more iteration to ensure we have the accuracy needed. For our third iteration, x3 is approximately 1.4142. This time, when we plug it in, our result, x4, is also approximately 1.4142. Since our approximation hasn't changed to 2 decimal places, we have our answer. Rounding to 2 decimal places, we get 1.41, and we can verify this with the memo. This example successfully demonstrates the iterative nature of Newton's method. You now know how to apply the formula and repeat the process until you achieve the required accuracy. Our next application of differentiation is optimization. In this scene, you will learn the general procedure for finding the maximum or minimum values of a function, which are often called optimum values. Optimization is about finding the absolute maximum or minimum value of a function. This has countless applications in engineering, business, and science. The foundation for this lies in a crucial property of functions. The derivative of a function is zero when that function reaches a local maximum or a local minimum. Think about it. At the peak of a hill or the bottom of a valley, the tangent line to the curve is horizontal, and a horizontal line has a slope of zero. This gives us a clear strategy for finding these points. Here is a step-by-step guide. First, we set up our objective function. This is the equation we want to maximize or minimize. Second, we find the first derivative of that function, f prime of x. Third, we set the first derivative equal to 0 and solve for x. The solutions are called critical points. These are our potential maximums or minimums. Great. We've found where the maximums or minimums could be. But how do we know if a critical point corresponds to a maximum or a minimum? That's where the second derivative test comes in. This is our fourth step. We find the second derivative, f double prime of x. If the second derivative is negative at a critical point, the function is concave down at that point, which means it's a local maximum. Conversely, if the second derivative is positive, the function is concave up, and we have a local minimum. A special case is when the second derivative is 0. In this situation, the test is inconclusive, and you'd have to use a different method, like the first derivative test. So, to recap, we've outlined a robust 5-step method for solving any optimization problem. You can now articulate the procedure for finding optimum values of a function using calculus. Let's put our optimization procedure to work with a practical example. By the end of this scene, you will be able to apply the 5-step process to solve a real-world optimization problem. Here's a classic problem. It involves finding the best possible dimensions for a box to maximize its volume. The question asks for the dimensions of an open box with a square base made from 1,200 square centimeters of material that will maximize the box's volume. This sounds like a maximum volume problem, so we'll need to use our 5 steps. The first step is to draw a diagram. Here's our box. Let the side length of the square base be x, and let the height of the box be y. Now let's write the equation we want to optimize, the volume v. Step 2. The objective function. The volume of a box is base area times height. Our base is a square of side x, so the area is x squared. The volume v is x squared times y. Notice we have 2 variables here, x and y. To differentiate, we need the volume to be a function of only one variable. For that, we'll use the constraint given in the problem, the material, the constraint function. The box uses 1,200 square centimeters of material, which is the surface area. The surface area of this open box is the area of the base, x squared, plus the area of the 4 sides, each being x times y. So x squared plus 4xy equals 1,200. Now we solve the constraint for one variable and substitute it into the volume equation. It's easier to solve for y. We get y equals the quantity 1,200 minus x squared, all divided by 4x. Now we substitute this expression for y into our volume equation. Our volume v is now a function of just x. V of x equals 300x minus x cubed over 4. This is the function we need to maximize. We have successfully completed step 1 of our general procedure. Now for step 2, find the derivative. The derivative of v with respect to x v prime of x is 300 minus 3/4 x squared. And step 3, set the derivative to 0. We set 300 minus 3 over 4 bars squared equals 0. Solving for x, we get x squared equals 400, which gives us 2 solutions. X equals 20 and x equals negative 20. Since x represents a length, we must discard the negative value. So, our only critical point is x equals 20 centimeters. We're almost there. Now we need to confirm that x equals 20 is a maximum. For that, we'll use the second derivative test, which is steps 4 and 5 of our procedure. Step 4. Find the second derivative. The derivative of 300 minus 3 over 4 pi squared is just negative 3 over 2 pi. Finally, step 5. Evaluate the second derivative at our critical point. When x is 20, v double prime of 20 is negative 30. Since the second derivative is negative, the second derivative test tells us that we have a local maximum at x equals 20. This confirms our x value for the largest possible volume. We're asked for the dimensions, so we need to find y as well. We use our constraint equation. Using y equals the quantity 1200 minus x squared, all divided by 4x, and substituting x equals 20, we get y equals 10. The dimensions for maximum volume are a 20 centimeter by 20 centimeter base and a 10 centimeter height. The dimensions are 20 centimeters by 20 centimeters by 10 centimeters, and we can verify this with the memo. Excellent. We have now walked through a complete optimization problem, from setting up the equations to using the second derivative test to find the answer. You can now confidently apply the optimization procedure. Our third application is related rates of change. By the end of this scene, you will understand the core idea of related rates and be able to set up equations for them. Related rates is about finding the rate at which one quantity is changing based on the rates of change of other related quantities. The fundamental principle is that we can differentiate both sides of a geometric equation with respect to time, t. The core rule is this. If the variables in an equation, like x and y, are also functions of time, we can differentiate the entire equation with respect to time, t, to get an equation with related rates. Let's see this in action with a simple example. Imagine a circular pond where a rock is thrown, causing circular ripples that spread outwards. The area of a circle is a equals pi r squared. The area a and the radius r are both changing with time. We want to find the relationship between their rates of change. To do this, we differentiate the equation a equals pi r squared, but not with respect to r. We differentiate with respect to time, t. On the left side, the derivative of a with respect to t is simply dA dt. This is the rate at which the area is changing. On the right side, we differentiate pr squared with respect to t. We use the chain rule here. First, we differentiate with respect to r to get 2 pi r, and then we multiply by d cos or c dash d, which is the derivative of r with respect to tt. This term, dr dt, is the rate at which the radius is changing. And there you have it. The equation dA dt equals 2 pir d relates the rate of change of the area to the rate of change of the radius. This is a related rates equation. So, to recap, we've established that related rates problems involve variables that are functions of time. The key is to differentiate the primary relationship equation with respect to time, t, using the chain rule. You can now define what related rates are and explain the method used to find them. Let's work through a classic related rates problem. In this scene, you will apply the steps for solving a related rates problem to a cone-shaped tank. This problem involves a conical tank and finding the rate at which the water level is rising. It will require us to find an equation relating the radius, height, and volume of the water. The question describes an inverted conical tank, 16 feet high and with a radius of 4 feet, being filled with water at a rate of 2 cubic feet per minute. We need to find how fast the water level is rising when the water is 8 feet deep. First, as always, let's draw the diagram. Here's our tank. We'll let r be the radius of the water's surface and h be the water's height. Both r and h are functions of time. Let v be the volume of the water. We are given that dv dt, the rate of change of volume, is 2 cubic feet per minute. We want to find dht, the rate of change of height, when the height h is 8 feet. Let's summarize the given information in the language of derivatives. Now, step 1 of the procedure is to find the primary equation. In this case, it's the volume of a cone. Step 1. The volume formula, blue, is V equals 1/3 pi r squared h. Again, we have two variables, r and h. We need a way to relate them. We can use similar triangles. From our diagram, the ratio of the water's radius to its height, r over h, must be the same as the ratio of the tank's radius to its height, which is 4 over 16. This simplifies to 1/4, so we get the constraint r equals 1/4 h. Now we substitute this constraint into our volume formula. Substituting r equals h over 4 into the volume formula gives v equals 1/3 pi times the quantity h over 4 squared times h. This simplifies to v equals 1/48 ph cubed. Our volume is now a function of height only. Excellent. We're ready for step 4. Differentiate with respect to time. Differentiating both sides with respect to t gives dv dt equals 1/16 ph squared dt. This is our related rates equation. Finally, step 5. Substitute the known values and solve. We know dv dt is 2, and we're interested in the moment when h is 8. Plugging these into our equation, we get 2 equals 1/16 pi times 8 squared times dh dt. Simplifying the right side, 8 squared is 64, and 64 divided by 16 is 4. So we have 2 equals 4p times dhd. Solving for dh wash dt, we get 1 over 2 pi feet per minute. This is the rate at which the water level is rising, and we can verify this with the memo. And there you have it. We've successfully solved a complex related rates problem. We used our 5-step method, diagram, primary equation, constraint, differentiation, and substitution. You are now able to apply this method to solve related rates problems. Our final topic is rates of change in motion. By the end of this scene, you will be able to relate a particle's displacement, velocity, and acceleration using derivatives. Here we connect calculus to the physics of motion, specifically rectilinear or straight line motion. This section introduces 3 key terms that are central to describing movement. These terms are displacement, velocity, and acceleration. They form a chain that we can navigate using derivatives. First, displacement. We'll denote it by s as a function of time, t. Think of displacement as the position or location of the particle relative to a fixed starting point. Velocity, which we'll call v of t, is the rate of change of displacement. In other words, velocity is how fast the position is changing. It's the first derivative of displacement. Finally, acceleration, a of t. Acceleration is the rate of change of velocity. It's how fast the velocity is changing. This means acceleration is the first derivative of velocity, and therefore the second derivative of displacement. So we have a clear hierarchy. You differentiate displacement to get velocity, and you differentiate velocity to get acceleration. Conversely, to go backwards, you integrate. Let's quickly define speed. Speed is not the same as velocity. Velocity is a vector and tells you both magnitude and direction. Speed is a scalar and only tells you the magnitude. For rectilinear motion, speed is the absolute value of the velocity. It's also important to understand the signs. A positive displacement means you're to the right of the origin, and a negative means you're to the left. A positive velocity means you're moving right, and a negative means you're moving left. A positive acceleration means you're speeding up if velocity is also positive, or slowing down if velocity is negative. To recap, we've established the fundamental links between displacement, velocity, and acceleration using differentiation. You now understand how the first derivative of displacement gives velocity, and the second derivative gives acceleration. Now let's apply our knowledge of motion. By the end of this scene, you will be able to analyze the motion of a particle by calculating its velocity and acceleration from a displacement function and interpreting their signs. Let's consider a simple scenario where a particle moves along a straight line. We'll be given its position and asked to find its other properties. The question gives us the displacement function for a particle. S of t equals 3t cubed minus 24t squared plus 36t. We need to find the acceleration and its velocity after 1 second. Let's tackle part A first, finding the acceleration function. Remember, acceleration is the second derivative of displacement. Here's our displacement function, s of t. The first derivative gives us the velocity v of t, which is 9t squared minus 48t plus 36. Now we differentiate the velocity function to find the acceleration, ai of t. The derivative of v of t is 18t minus 48. So, the acceleration at any time t is 18 minus 48 meters per second squared, and we can verify this with the memo. Great. Now for part B, finding the velocity at t equals 1 second. We'll use the velocity function we just found. Here is our velocity function again. To find the velocity at 1 second, we simply substitute t equals 1 into the equation. This gives us v of 1 equals 9 minus 48 plus 36, which is negative 3. So, the velocity after 1 second is negative 3 meters per second. This means the particle is moving to the left at a speed of 3 meters per second. We can verify this with the memo. Let's explore this motion a bit further. When is the particle at rest? A particle is at rest when its velocity is 0. We set our velocity function to 0 and solve for t. We can factor the equation to get t equals 2 and t equals 6. The factorization in the memo is slightly different. The memo shows t equals 2 and t equals 6. Let's use those values for our analysis. At t equals 2 and t equals 6 seconds, the particle momentarily stops before changing direction. Let's quickly check the acceleration at these times. At t2, a 2 equals 18.2, 48 equals 36, 48 equals 12. A negative acceleration while moving right, t2, or just starting to move left, tt2, makes sense. The particle is slowing down or changing direction. At tt6, a 6 equals 18.6, 48 at 108, 48 equals 60. A positive acceleration at t6 means it's speeding up in the positive direction or continuing to slow down if the velocity was negative just before t6. Wait, if it stopped at t6, it must have been moving left and now is accelerating right to start moving right again. In this scene, you have successfully calculated the velocity and acceleration functions from a displacement function and evaluated them at a specific time. You are now equipped to describe the motion of a particle based on its position function. Let's summarize everything we've learned in this module on applications of differentiation. In this final scene, you will review and consolidate the key techniques we've covered. We started by looking at 4 powerful applications of the derivative. First, we explored Newton's method, a systematic process to find better approximations for the roots of an equation. We then moved to optimization, which involves finding the maximum or minimum values of a function using the first and second derivatives. Next, we tackled related rates of change, where we differentiated equations with respect to time to find the relationship between changing quantities. Finally, we connected calculus to physics by analyzing motion in a straight line, understanding how derivatives link displacement, velocity, and acceleration. In each case, you learned a structured step-by-step procedure to follow, ensuring you can tackle a wide range of problems. From numerical approximation to designing optimal solutions and describing motion, the derivative is an incredibly versatile tool. Remember, the key to success with these applications is practice. Work through more examples, apply these methods, and you'll build your confidence and understanding. Thank you for joining this tutorial. Subscribe for more tutorials from Math Zone African Motives.